Hello everyone, this is me, Ms. Rachel Betty, Assistant Professor in the Department of BCA, Bishop Heber College, Tiruchirappalli. Welcome to the first unit of Fundamentals of Deep Learning. There are some contents which falls under Unit 1. From the next slide, we'll see the contents which we are going to study in this video. So these are the contents which falls under Unit 1. First topic is what is deep learning, artificial intelligence, machine learning and deep learning. Artificial intelligence, what it talks about, and machine learning. Learning representations from data, the word deep in deep learning. Understanding how deep learning works, data preliminaries, data manipulation, operations, broadcasting mechanism, indexing and slicing, data pre-processing, reading the data set, and handling missing data. Now we'll move to the next slide. What you see is a pictorial representation of what is an artificial intelligence, a machine learning and a deep learning. As you can see from this picture says that deep learning is the brain of a model which is going to make the artificial intelligence work. And machine learning is the subset of deep learning. And deep learning is the subset of artificial intelligence. So from this picture we can understand that both the machine learning and deep learning work together or make the artificial intelligence work, where the artificial intelligence is going to be the working part of the model. Now we'll move to the next slide, which talks about what is deep learning. It is a subset of machine learning and artificial intelligence. The deep learning trains the model using large data sets. This training is done using multiple layers. The deep learning uses neural networks with many layers to analyze data. Deep learning is a subset of machine learning that uses a multi-layered neural networks called deep neural networks to simulate the complex decision-making power of the human brain. It is a field of artificial intelligence that focuses on using neural networks with many layers to analyze various forms of data. Deep learning models, particularly artificial neural networks, which we call as ANNs, are designed to automatically learn and improve from data without explicit programming, mimicking the structure and functioning of the human brain. The deep learning is especially powerful for tasks that involve large amounts of data, such as intelligent chatbots, which we are famous these days, self-driving cars, virtual assistants, image recognition, natural language processing, and speech recognition. And deep learning, its ability to learn hierarchical features from data, makes it highly effective in capturing complex patterns. Now we'll move on to the next slide, which talks about the applications where this deep learning is applied. The first application where it is applied is in the computer vision. In computer vision, deep learning models enable machines to identify and understand visual data. Some of the main applications of deep learning in computer vision include object detection and recognition. Deep learning models are used to identify and locate objects within images and videos, making it possible for machines to perform tasks such as self-driving cars, surveillance, and robotics. In computer vision, we have image classification where deep learning models can be used to classify images into categories such as animals, plants, and buildings. This is used in applications such as medical imaging, quality control, and image retrieval. There's another application in computer vision which is called an image segmentation, where deep learning models are used for image segmentation into different regions, making it possible to identify specific features within images. The next application is natural language processing, which is called NLP. In NLP, deep learning model enable machines to understand and generate human language. Some of the main applications of deep learning in NLP include automatic text generation. Deep learning model can learn the corpus of text and new text like summaries, essays, which can be automatically generated using these trained models. Language translation. In deep learning models, it can translate text from one language to another, making it possible to communicate with people with different linguistic backgrounds. Then comes sentiment analysis under NLP, where deep learning models analyze the sentiment of a piece of text, making it possible to determine whether the text is positive, negative, or neutral. Speech recognition is the another application in NLP, where deep learning models recognize and transcribe spoken words, making it possible to perform tasks such as speech to text conversion, voice search, and voice controlled devices. So next, we have reinforcement learning, where the deep learning is applied. In reinforcement learning, deep learning works as training agents to take action in an environment to maximize a reward. Some of the main applications of deep learning in reinforcement learning include game playing. Deep reinforcement learning models have been able to beat human experts at games such as Go, chess, and Atari. Robotics. Deep reinforcement learning models can be used to train robots to perform complex tasks such as grasping objects, navigation, and manipulation. Then comes control systems. Deep reinforcement learning models can be used to control complex systems such as power grids, traffic management, and supply chain optimization. Challenges in deep learning. Deep learning has made significant advancements in various fields, but there are still some challenges that need to be addressed. Here are some of the main challenges in deep learning. Number one comes data availability. It requires large amounts of data to learn from. For using deep learning, it is a big concern to gather as much data for training. The second one comes as computational resources. For training the deep learning model, it is computationally expensive because it requires specialized hardware like GPUs and TPUs. Time consuming. While working on sequential data depending on the computational resource, it can take very large, even in days or months. Interpretability. Deep learning models are complex. It works like a black box. It is very difficult to interpret the result. Overfitting. When the model is trained again and again, it becomes too specialized for the training data, leading to overfitting and poor performance on new data. We'll see advantages of deep learning. The number one advantage we see is the high accuracy. Deep learning algorithms can achieve state-of-the-art performance in various tasks such as image recognition and natural language processing. Automated feature engineering. Deep learning algorithms can automatically discover and learn relevant features from data without a need for manual feature engineering. Scalability. Deep learning models can scale to handle large and complex data sets and can learn from massive amounts of data. Flexibility. Deep learning models can be applied to a wide range of tasks and can handle various types of data such as images, text, and speech. Continual improvement. Deep learning models can continually improve their performance as more data becomes available. Now we'll see the disadvantages of deep learning. The high computational requirements becomes the first disadvantage of deep learning. Deep learning AI models require large amounts of data and computational resources to train and optimize. Also, it requires large amounts of labeled data. Deep learning models often require a large amount of labeled data for training, which can be expensive and time-consuming to acquire. Interpreting ability. Deep learning models can be challenging to interpret, making it difficult to understand how they make decisions. Overfitting. Deep learning models can sometimes overfit to the training data, resulting in poor performance and new and unseen data. Black box nature. Deep learning models are often treated as black boxes, making it difficult to understand how they work and how they arrived at their predictions. The next slide talks about the artificial intelligence, machine learning, and deep learning. With the picture, you can understand the relationship between AI, ML, and deep learning. Artificial intelligence. It is a broad field that aims to create machines capable of intelligent behavior, including reasoning, problem solving, and decision making. AI includes various subfields such as robotics, expert systems, and natural language processing. Machine learning, it is a subset of AI that involves using algorithms, statistical models to allow computers to learn from data, improving performance over time without being explicitly programmed. Machine learning algorithms can classify data, make predictions, and even identify patterns from vast amounts of data and also learns from data. Deep learning, it is a subset of machine learning that uses artificial neural networks with many layers. Deep learning models are designed to learn from large unstructured data sets such as images, text, and speech, and automatically detect complex patterns in the data. Now we come to the artificial intelligence. It refers to the technology that allows machines and computers to replicate human intelligence. It enables a system to perform tasks that require human-like decision-making, such as learning from data, identifying patterns, making informed choices, and solving complex problems. It improves continuously by utilizing methods like machine learning and deep learning. It is commonly found in everyday applications such as chatbots, recommendation systems like Netflix, YouTube, self-driving cars, and voice assistants like Siri, Alexa. It enhances efficiency by automating tasks and reducing human effort. In real-world applications, artificial intelligence is used in healthcare for diagnosing diseases, finance for fraud detection, e-commerce for personalized recommendations, and transportation for self-driving cars. It also powers virtual assistants like Siri and Alexa, chatbots for customer support, and manufacturing robots that automate production processes. It refers to the simulation of human intelligence in machines that are programmed to think, reason, learn, and act like humans. AI refers to the development of computer systems capable of performing tasks that typically require human intelligence. These tasks include recognizing visual perception, speech recognition, decision making, language translation, solving problems, and identifying patterns. AI encompasses a wide range of technologies, including machine learning, deep learning, and natural language processing, expert systems, computer vision, and robotics. Artificial intelligence was born in the 1950s. Whether computers could be made to think, the effort to automate intellectual tasks normally performed by humans. AI is a general field that encompasses machine learning and deep learning. Early chess programs, hard-coded rules crafted by programmers qualify as machine learning. How does AI work? AI works by simulating human intelligence in machines through algorithms, data, and models that enable them to perform tasks that would typically require human intervention. Here is a simplified breakdown. First, it collects data. AI systems rely on vast amounts of data. This data can come from various sources like images, text, or sensor readings. For example, we are building an AI that recognizes cats in images. We need a large data set of labeled images of cats. Processing and learning. Machine learning, a subset of AI, uses algorithms to analyze the data. The system learns patterns from the data by training a model. For instance, an AI system might learn features of cat like its shape, ears, and whiskers by being exposed to thousands of labeled images of cats and non-cats. Model training. The AI model undergoes training using the data. In this process, the model adjusts its parameters based on the input data and the desired output. The more data and training time, the more accurate the model becomes. Making decisions. After training, the AI can make decisions and predictions based on new unseen data. For example, it might predict whether an image contains a cat based on the patterns it learned from the previous training data. Feedback and improvement. In many AI systems, particularly in reinforcement learning, feedback is used to improve performance over time. The system's actions are continuously evaluated and adjustments are made to improve future performance. The following are the types of AI. It can be classified into two main categories based on its capabilities and functionalities. Number one, based on capabilities. Weak AI, which is also called as narrow AI. This type of AI is designed to perform a specific task or a narrow set of tasks such as voice assistance or recommendation systems. It excels in one area but lacks general intelligence. Strong AI, or we call it as general AI, it is a theoretical concept where AI can perform any intellectual tasks that a human can do. It demonstrates human-like reasoning and understanding across multiple domains, making it capable of tackling a wide variety of tasks. Super intelligent AI. It is a hypothetical form of AI that would surpass human intelligence in all areas. It would be capable of performing tasks more efficiently and effectively than humans. Then AI based on functionalities. Reactive machines. Reactive machines are AI systems that respond to specific tasks or situations but do not store memories or improve over time. They are programmed to react in a fixed way without learning from past experiences. Limited memory. Limited memory AI can store and learn from past experiences to make better decisions in the future. Self-driving cars are an example, as they use historical data to navigate and adapt to changing environments. Theory of mind. The theory of mind is a typical theoretical type of AI that would be able to understand emotions, beliefs, intentions, and other mental states. This would allow the AI to interact with humans in a more natural and empathetic manner. Self-aware AI. It is a hypothetical form of AI that possesses consciousness and self-awareness. It would have an understanding of its own existence and could make decisions based on that awareness. Benefits of AI. The widespread uses of AI has brought numerous advantages across various sectors and aspects of our daily lives. Here are some of the primary benefits of AI. Number one, efficiency and automation. AI can automate repetitive tasks, reducing human error and saving time. This leads to increased productivity and allows humans to focus on more complex tasks. Improved decision making. AI can analyze vast amounts of data quickly and provide insights, helping business and organizations make better data-driven decisions. Personalization. AI can be used to offer personalized experiences in areas like retail, entertainment, and online services, improving user satisfaction. For example, recommendation systems on platforms like Netflix or Amazon suggest products or content based on individual preferences. 24/7 availability. Unlike humans, AI systems can operate around the clock without breaks. This is particularly useful in customer support, monitoring, and other services that require constant attention. Data analysis and pattern recognition. AI excels at processing large data sets and recognizing patterns that may be difficult for humans to identify. This is especially beneficial in fields like healthcare, finance, and marketing. Symbolic AI. Experts believe that human-level artificial intelligence could be achieved by having programmers handcraft a sufficiently large set of explicit rules for manipulating knowledge. This approach is known as symbolic AI. It is used to solve well-defined logical problems such as playing chess, but it is difficult to find explicit rules for solving more complex, fuzzy problems such as image classification, speech recognition, and language translation. Machine learning. Machine learning is a field of artificial intelligence that enables computers to learn from data and improve their performance without being explicitly programmed. It involves algorithms that can analyze patterns, make predictions, and learn from experience, allowing systems to autonomously adapt and improve their accuracy over time. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if its performance at tasks in T as measured by P improves with experience E. Machine learning is the study of algorithms that improve their performance at some tasks with experience. Where well-defined learning task is given by P stands for performance, task T, and experience E. In Victorian England, Lady Ada Lovelace was a friend and collaborator of Charles Babbage, the inventor of the analytical engine, the first known general-purpose mechanical computer. Computing machinery and intelligence, which introduced the Turing test as well as key concepts that would come to shape AI. Alan Turing arises the questions asking whether general-purpose computers could be able or capable of learning, and he came to the conclusion that they could. Machine learning arises from this question. Could a computer go beyond what we know how to order it to perform and learn on its own how to perform a special task? Could a computer surprise us? Rather than programmers crafting data processing rules by hand, could a computer automatically learn these rules by looking at data? In classical programming, humans input rules and data to be processed according to these rules and come the answers. With machine learning, humans input data as well as the answers expected from the data and outcome the rules. These rules can then be applied to new data to produce original answers. So, this is the representation of machine learning, which is a new programming paradigm. We give rules and data which gives you an output in classical programming. But machine learning programming gets the input of data and answers, which gives rules as an output. So in traditional programming, we give data, program. We feed it inside the computer, and the computer processes the data on the program and gives us the output. In machine learning, we give data and output as the input to the computer system, and the system performs the data and output and gives us the rules, which is called a program. A machine learning system is trained rather than explicitly programmed. It's presented with many examples relevant to a task, and it comes up with the rules for automating the task. For example, if we wish to automate the task of tagging our vacation pictures, we could present a machine learning system with many examples of pictures already tagged by humans. And the system will learn statistical rules for associating specific pictures to specific tags. Machine learning tends to deal with the large, complex data sets, such as a data set of millions of images, each consisting of tens of thousands of pixels. Learning representations from data. Machine learning discovers rules to execute a data processing text. Machine learning, we need three things: input data points. For instance, if the task is speech recognition, these data points could be sound files of people speaking. If the task is image tagging, they could be pictures. Examples of the expected output in a speech recognition task, these could be human-generated transcripts of sound files. In an image task, expected outputs could be tags such as a dog, cat, and so on. A way to measure whether the algorithm is doing a good job, this is necessary in order to determine the distance between the algorithm's current output and its expected output. The measurement is used as a feedback signal to adjust the way the algorithm moves. This adjustment step is what we call learning. A machine learning model transforms its input data into meaningful outputs, a process that is learned from exposure to known examples of inputs and outputs. Therefore, the central problem in machine learning and deep learning is to meaningfully transform data, to learn useful representations of the input data at hand, representations that get us closer to the expected output. What is a representation? At its core, it is a different way to look at data to represent or encode data. For instance, a color image can be encoded in the RGB format or in the HSV format. These are two different representations of the same data. Some tasks that may be difficult with one representation can become easy with another. For example, the task select all red pixels in the image is simpler in the RGB format, whereas make the image less saturated is simpler in the HSV format. Machine learning models are all about finding appropriate representations for their input data. Transformations of the data that make it more amenable to the task at hand, such as a classification task. From this picture, some sample data is given here in this figure, where you have white dots and black dots in XY. Consider an x-axis and y-axis. Some points represented by the coordinates in the XY system. We have few white points and a few black points. Let's say we want to develop an algorithm that can take the coordinates xy of a point and output whether that point is likely to be black or to be white. In this case, the inputs are the coordinates of our points. The expected outputs are the colors of our points. A way to measure whether our algorithm is doing a good job could be, for instance, the percentage of points that are being correctly classified. What we need here is a new representation of our data that clearly separates the white points from the black points. One transformation we could use among many other possibilities would be a coordinate change, which is given the next figure. So we see a coordinate change here in this picture. We have the raw data or xy coordinates. We slightly change the coordinate. So as we are going to change the coordinates, as the process is getting into a better representation where it clearly separates white dots from the black dot. In this new coordinate system, the coordinates of our points can be said to be new representation of data. With this representation, the black or white classification problem can be expressed as a simple rule. Black points are such that x is greater than 0 or white points are such that x is less than 0. This new representation basically solves the classification problem. In this case, we define the coordinate change by hand. But if instead we tried systematically searching for different possible coordinate changes and used as feedback the percentage of points being correctly classified, then we would be doing machine learning. Learning in the context of machine learning describes an automatic search process for better representations. All machine learning algorithms consist of automatically finding such transformations that turn data into more useful representations for a given task. These operations can be coordinate changes or linear projections, which may destroy information, translations, non-linear operations such as select all points such that x is greater than 0 and so on. Machine learning algorithms search through a predefined set of operations called hypothesis space. Machine learning is searching for user representations of some input data within a predefined space of possibilities using guidance from a feedback signal. This simple idea allows for solving a remarkably broad range of intellectual tasks, from speech recognition to autonomous car driving. AI aims to make machines intelligent. Machine learning focuses on algorithms that allow machines to learn from data. Deep learning involves learning multiple levels of representation from raw data using deep neural networks. For example, in deep learning, raw data such as image can be processed through layers of a neural network where each layer learns increasingly complex features. Example, edges, textures, objects. The word deep in deep learning. Deep learning is a specific subfield of machine learning, a new intake on learning representations from data that puts an emphasis on learning successive layers of increasingly meaningful representations. The deep in deep learning isn't a reference to any kind of deeper understanding achieved by the approach. Rather, it stands for this idea of successive layers of representations. How many layers contribute to a model of the data is called the depth of the model. Other appropriate names for the field could have been layered representations learning and hierarchical representations learning. Modern deep learning often involves tens or even hundreds of successive layers of representations, and they are all learned automatically from exposure or to training data. Meanwhile, other approaches to machine learning tend to focus on learning only one or two layers of representations of the data. Hence, they are sometimes called shallow. In deep learning, these layered representations are almost or always learned via models called neural networks, structured in literal layers stacked on top of each other. Deep learning is the mathematical framework for deep learning representations from data. What do the representations learned by a deep learning algorithm look like? Let's examine how a network several layers deep transforms an image of a digit in order to recognize what digit it is. We'll see with the picture representations to come in the first. So this is an original input of a picture where it passes 4 layers. The final input is given as a digital classification. So it's a deep neural network for digital classification. Example. As you can see in the above picture, the network transforms a digit image into representations that are increasingly different from the original image and increasingly informative about the final result. A deep network has a multi-stage information where information goes through successive filters and comes out increasingly purified, that is, useful with regard to some task. So we will move on. So these are how the deep learning represent an original input into digital forms. So layer 1, the original image has been split into some split images, and layer 2, it more splits the image into black and white spots. Now in layer 3 we can clearly say where all the white spots are and where are the black spots are, and in layer 4, in the final output, we get the digital information about the original input that has been given to the layer 1. So deep learning is a multi-stage way to learn data representations. Deep networks use many layers to extract complex hierarchical representations from data. Example, from edges in an image, that is low level, to objects or faces, that is high level. Power enables solving complex problems that traditional methods cannot. Understanding how deep learning works. Machine learning is about mapping inputs such as images to targets such as label cat, which is done by observing many examples of input on targets. Deep neural networks do this input to target mapping via a deep sequence of simple data transformations, and that these data transformations are learned by exposure to example. The specification of what a layer does to its input data is stored in the layer's weights, which represents a bunch of numbers. The transformation implemented by a layer is parameterized by its weights. Weights are also sometimes called the parameters of a layer. Learning means finding a set of values for the weights of all layers in a network, such as that the network will correctly map example inputs to their associated targets. A deep neural network can contain tons of millions of parameters. Finding the correct value for all of them may seem like a daunting task, especially given that modifying the value of one parameter will affect the behavior of all the others. So finding the right values for these weights, we give input as x. This goes into data transformation and it comes out as a prediction. So it is a neural network is parameterized by its. To control something, first you need to be able to observe it. To control the output of a neural network, you need to be able to measure how far this output is from what you expected. This is the job of the loss function of the network, also called the objective function. The loss function takes predictions of the network on the true target, what you wanted the network to output, and computes a distance score capturing how well the network has done on this specific example. It is represented in the picture as a loss function gives a loss. The fundamental trick in deep learning is to use this score as feedback signal to adjust the value of the weights a little in a direction that will lower the loss score for the current exam. This adjustment is the job of the optimizer, which implements what is called the back propagation algorithm. The central algorithm in deep learning, neural networks, layers of neurons that process data. Forward propagation, data flows through layers to generate predictions. Back propagation adjusts model weights to reduce errors. Activation functions are called decide whether to pass data to the next layer. So you see in this flow of chart that the loss score is given again as the feedback as an optimizer to the optimizer. Then it adjusts the weight. The weight is updated and the loss function is calculated. Initially, the weights of the network are assigned random values. So the network merely implements a series of random transformations. Naturally, its output is far from what it should really ideally be, and the loss score is accordingly very high. But with every example, the network processes the weights are adjusted a little in the correct direction and the loss score decreases. This is the training loop, which repeated a sufficient number of times, typically tens of iterations, over thousands of examples, yields weight values that minimize the loss function. A network with minimal loss is one for which the outputs are as close as they can be to the targets at training. The deep in deep learning refers to the use of many layers of neural networks, which enables the model to learn and extract complex hierarchical representations from raw data. This depth allows the model to learn from low-level features, like edges in an image, to higher-level abstraction, example, faces or objects in the image. The deeper the neural network, the more complex patterns it can learn. These deep networks, composed of many layers of interconnected neurons, have been shown to outperform traditional machine learning methods on many complex tasks like image and speech. Neural networks. Deep learning models use artificial neural networks, which are composed of layers of nodes called neurons. Each neuron processes input data, applies a mathematical transformation, and passes the output to the next layer. Forward propagation. When a data set is fed into the network, the data flows through the layers, with each layer learning progressively more abstract features from the data. The final layer produces predictions or classifications. Backpropagation. The model learns by comparing its predictions and the actual result and adjusting the weights of the connections between neurons to minimize the error. This is done using an algorithm called backpropagation, which updates the weights based on the gradient of the error. Activation functions. Each neuron applies an activation function to decide whether to pass new information to the next layer. Common activation functions include rectified linear unit, sigmoid, and tangent. Terminologies related to deep learning. Neural networks. Neural networks mimic the working of human brain. Information flows from one neuron to another via axon or first to dendrites of the other. In neural networks, neuron, that is nodes, receives input signal, input values, which passes through neuron and delivers output signal. This is an example of deep neural network. Deep neural networks components are input layer, hidden layer, activation function, and output layer. Deep neural networks activation functions are ReLU, tanh, sigmoid, softmax. This is a representation of input image 3 by 3 pixels as an digital images. How they are converted, the output prediction, how the output prediction would be. Deep neural network flow. Training data include target output are given as features to model, and the output is a predicted target where it computes a loss, and it gives an optimized result where it gives us a feedback to the model. Frameworks for deep learning: TensorFlow, Keras, Python, DL4J, Caffe are these. Applications of deep learning, we have already seen that application in the first few slides. Again, we'll go with the applications like self-driving cars, news aggregation and fraud, news detection, virtual assistants, healthcare, detect development delay in children, automatic game playing, adding sounds to silent movies, automatic machine translation, deep dreaming, demographic and election predictions. Data preliminaries. To prepare for your device into deep learning, you will need a few survival skills, where techniques for storing and manipulating data, libraries for ingesting and pre-processing data from a variety of sources, knowledge of the basic linear algebraic operations that we apply to high-dimensional data elements, calculus to determine which direction to adjust each parameter in order to decrease the loss function, the ability to automatically compute derivatives so that you can forget much of the calculus you just learned. Some basic fluency in probability, our primary language for reasoning under uncertainty, and some aptitude for finding answers in the official documentation when you data manipulation. There are two important things we need to do with data. one, acquire them, two, process them once they are inside the computer. There is no point in acquiring data without some way to store it. Tensors. N-dimensional arrays, which we also call tensors. For all modern deep learning frameworks, the tensor class resembles NumPy's ND array with a few killer features added. The tensor class supports automatic differentiation. It leverages GPUs to accelerate numerical computation, whereas NumPy only runs on CPUs. These properties make neural networks both easy to code. Thank you for listening patiently, and we have come to the end of Fundamentals of Deep Learning of Unit 1. I hope that you find it useful. Thank you very much.